Hello guys, welcome to another video in the series of coding. Today let's do the problem. It's called counting bits. So you are given an integer n, you have to return an array answer of length n plus 1 such that for each I, answer of I is the number of ones in the binary representation of I. Okay, so what do you have to do in the question? So let's say n is equal to 15. In the question what they are asking is you have to create a vector, right? You have to create a vector which is from 0 to 15, and in each of the numbers you have to tell how many ones are there. How many ones are there in the binary representation? For example, in 0 there is 0 ones, right? So you have to write 0. In 1 there is 1 1, right? So you have to write 1. In 2 there is 1 1, so again you have to write 1. In 3 there are 2 ones, so you have to write 2. In 4 there is 1 1 again, okay, so you have to write 1. In 5 there are 2 ones. In the binary representation of 5 there are 2 ones. In the binary representation of 6 there are again 2 ones. In the binary representation of 7 there are 3 ones. In the binary representation of 8 there is 1 1. For 9 it is 2. For 10 also it's 2. For 11 it is 3. For 12 it is 2. For 13 it is 3. For 14 it is 3. And for 15 it is 4, and so on, right? So you have to build this vector, and once you build this vector you have to return this as the answer. Okay, so let's see how we can solve it in the brute force approach. So what is the brute force approach? Just write all the numbers from 0 to n. Okay, for example, n is equal to 15. Write all the numbers from 0 to 15, and for each such number find out what is how many ones are there in the binary representation. How are you going to find the number of ones? For example, let's take an example. In 7, let's say you have the number 7. How are you going to find how many ones are there in the binary representation of 7? It's very simple, right? It's very simple. To find the number of ones, what are you going to do? Just take the last digit. Is it a 1? It's a 1, then increment it and count. Okay, so the last digit is a 1, right? So till now I have found 1 1. Okay, after you find the last digit, what are you going to do? Just remove the last digit. Okay, then your last digit gets shifted. Now see this digit. Is it a 1? Yes, it's a 1. So again increment your count. Okay, and then what you are going to do? You are going to remove this. Okay, again then what you are going to do? Similarly check this digit. Is it a 1 or it's a 0? It's a 1. Again it's a 1, right? So your count is going to become equal to 3. Then what you are going to do? You are going to remove this last digit also. Till the number becomes 0, you will keep on doing this. So finally the count is 3. So in the binary representation of 7, you have 3 ones. Okay, now let's code the brute force solution, and let's see what is the problem in the brute force solution. Okay, so let's start. The brute force solution is very simple. So we'll start from 0 to n, and okay, so what is the number that we have? The number that we have is I, right? We have I. So for example, okay, for example, let's take a bigger example just to be clear. Okay, let's say you have such number like this. You have to find how many ones are there in this binary representation, right? So how will you find? Till the number is non-zero, right? Till the number is non-zero, because a 0 number doesn't have any ones. Okay, so till the number is non-zero, what you will do? First of all, you will check if the last digit is a 1 or not. So how will you check that? Just do num mod 2. If num mod 2, if the last digit is 1, what is num mod 2? Num mod 2 will be 1. If the last digit is 0, if the last digit will be 0, num mod 2 will be 0. Okay, that's how you can check. So if num mod 2 is equal to 1, that means that last digit you have a 1, right? So you can simply give a count variable. Let's see, int count is equal to 0, and you can increment the count by just doing num mod 2. Okay, after this what you will do? So you have, let's say last digit is a 1, right? So till now my count is equal to 1. Next time what do you want to do? You want to remove this one. You have already taken its count is equal to 1. So now we will remove this. So how can we remove this? Just do num is equal to num by 2. Okay, that's it. If you divide by 2, so this was the original number that we have. If we divide it by 2, what we are doing? We are just shifting it. So we are removing the last digit, and this will become your number. Now again we will come here. What is the count? Now we will again check if this digit is a 1 or not. Here in our case this digit is also a 1, so count will increment by 1. Okay, then next we will again divide the number by 2. Next, this is our number. Now the last digit is 0, so count will not increment, so count will increment by 0. Okay, count will remain same. Again we divide the number by 2. Again we check if this digit is a 1. This digit is a 1, so our count will increment by 1. Okay, and then we divide the number by 2. Now this digit is 0, so our count will increment by 0. Again we divide the number by 2. Again now this digit is 1. That means what? That means that we can increment by 1. And now if we divide this number by 2, number becomes equal to 0. So while the number does not become equal to 0, we can keep doing this operation. When it becomes equal to 0, it will exit the loop. Okay, and now what you can do? So you have made, let's make an answer vector. Let's make an answer vector int answer n plus 1 and 0. Okay, Now answer of I will become equal to whatever count is there, and you can return answer. Okay, so this should work, but what is the problem with this brute force approach is its time complexity. So this will work, we'll submit and see it should work, but its time complexity is large. So we'll discuss what is the time complexity of this. So see, we are running this for loop, right? So this will run n times, but inside the for loop we are also doing this work. Okay, now how many times are we doing this work? We are dividing it by 2, right? So in the worst case, okay, so what's happening, since we are dividing it by 2, this log base 2, right? We are doing log base 2 work, and what is the maximum size? So n. So if you have a number, the last number will be n, right? So you can, this work will happen, it will take log of n work, right? And you are running this loop n times. So if you write the time complexity, it will be n log n. Okay, the time complexity will be n log n, because this inner loop will take log n, okay, in the worst case, and this will run n times. So this is the problem. So we want to do it in just O of n. We don't want to do this while loop. This is the while loop which is giving you extra time complexity. So we'll remove this, and let's see if we can just do it in O of n. Okay, we'll just do it in single for loop and in single pass and in just O of n. Okay, now let's see how we can do it in just O of n. Okay, so now see, you have to find the number of ones, right? Now observe something. So to find the number of ones, see, let's say, let me remove all this. Okay, let's say you want to find the number of ones in a number 6. Okay, in a number 6. So let's say, okay, let's say I start building the solution. Let me write the solution already up till 5. Okay, let me write the solution up till 5. So up till 5, let's say I already have my solution, right? I have built it. Now I want to find the answer for n equal to 6. How many ones are there in this? I want to find. Now observe something. What is this? This is 0, 1, 1, 0, right? This is 6. 6 is 0, 1, 1, 0. Okay, in 3 also. Okay, so this is 3. So 3 is just left shifted. Okay, 3 is just left shifted. So this is the binary representation for 3, and this is the binary representation for 6. So this is the binary representation for 3, this is the binary representation for 6. See, both of them are just same. The binary representation, both of them is same. It is just that 3 is okay. If you left shift 3, you will get 6. Okay, because 3 into 2, by left shift what we do, see, if you have any number, okay, let me take one more example. If you have any number, right, and you want to find the binary representation of 2 times that number, what you do, you just shift this number, right? What you do, you just shift this number, and you will be able to get the binary representation of 2 times n. Okay, so that is what the binary representation of 3 and 6 are very similar. Okay, except that this piece has got shifted and come here. Okay, so this is very important to understand. This piece was in the last, this piece has got shifted and it has come here. Okay, that is what is happening in the binary representation. Okay, so binary representation of 3 and 6 is very similar. Why am I telling this? Because number of ones already we have calculated in 3. Now I want to calculate number of ones in 6. So it's very similar. See, 3 also has 2 ones, 6 also has 2 ones. Number of ones are same because the binary representations are just the same, but it is just left shifted. But by left shifting, you are not changing the number of ones. Number of ones are going to remain the same, right? So 3 and 6 have the same number of ones. Okay, let's see this for other cases. Okay, very simple. Okay, very simple. See, what is the number of let's say I want to find the number of ones in 2. Okay, now let me look at the number of ones in 1. 1 also has 1, 1. And see, this is just getting left shifted. So observe the binary representation of 1 and 2 carefully. If 1 just gets left shifted, you are getting 2. So the number of ones in both of them are remaining same. 1 has 1, 1 and 2 also has only 1, 1. Okay, now let's look at the next case. Let's say I want to find the binary representation of 4. So I will just look at the number of ones in 2. Both of them will have the same number of ones, because what is happening, observe 2 and 4 very carefully. Only one left shift is happening, nothing else is happening. Number of ones is remaining same, right? So number of ones in 4 and 2 is also same. So let me fill it here. Okay, similarly, let's say I want to find the number of ones in 6. Okay, I will just look at the number of ones in 3. Okay, number of now 3 has 2 ones, so 6 will also have 2 ones. Okay, so it's very simple. See, 3 has 2 ones, so 6 will also have 2 ones. Okay, because what is happening, only this portion is getting left shifted, nothing else is changing. Okay, so that's it. Now Okay, so 6 also has 2 ones. Now similarly, let me try to find the binary representation number of ones in 8. Now let me just look at number of ones in 4. 4 has 1 1, so 8 also has 1 1. Okay, now let me try to observe this for all other examples. Okay, let me try to observe if I can make a pattern for all other examples. Okay, let me take any random number. Let me take any random number now. So let's say I want to find the number of ones in 12. What will I do? I'll look at the number of ones in 6, because see, what is 6? 6 is just this. If I just left shift it, this will become 12, right? This is 6, this is 12, but number of ones are going to remain same, so both of them have 2 ones. Okay, let me take another example. Let's say I have 14. What is the number of ones in 14? This is 14. Number of ones in 14 is 3. Now let me look at 7. What is 7? This is 7, because this portion has just got left shifted. Okay, so this is 7 and this is 14. Okay, so number of ones are same, both of them have number of ones 3. Okay, so the logic is very simple. Okay, logic is very simple. Number of ones, how can I calculate? If I have a number, I already have calculated the number of ones previously when I had, see, if I have a number n, I have already calculated the number of ones previously when I calculated n by 2, and the number of ones are going to be same in both of them. Okay, so this will be valid for what? For all even numbers this will be valid. Okay, it will not be valid for what? It will not be valid for odd numbers. Let's check for the case n equal to 15. So whenever you have odd numbers, what happens? See, whenever you have odd numbers, n is equal to 15. If you do n by 2, that is equal to 7, right? N by 2 is equal to 7. What is the binary representation of 7? 0, 1, 1, 1. So what is happening? What is the difference between 15 and 7? See, what is happening? You have 0, 1, 1, 1, right? And you are left shifting it. Okay, if you left shift this, you will be getting 14, but you need to add one extra one to make it to 15. Okay, so if you just simply left shift it, you will be getting n equal to 14. Just triple 1 will be 14, but you need to add one extra one to make it 15. Okay, so what is happening? See, very simple. Let's understand it again. Let me take one more example. Okay, let's say you want to find the number of ones in n equal to 11. Okay, what is n equal to 11? N equal to 11 is 1, 0, 1, 1. How many ones are there? 3 ones are there. So what we'll do, we'll look at n by 2, because we have already saved the answer for n by 2. So we need not calculate the answer again. We already know the answer for n by 2. What is n by 2? N by 2 is 5. What's the binary representation of 5? 1, 0, 1. Okay, so how many ones are there in 5? 2 ones are there in 5. So what we'll do, we are just left shifting 5, right? We get this value, but in the end, okay, so this is n equal to 10, it also has 2 ones, because 5 also has 2 ones, so 10 also has 2 ones. But if we add one more one, we will be able to reach what? We will be able to reach 11. So whenever you have an odd number, right, look at n by 2, but also add one extra one. Okay, that is a simple logic. Okay, now let's build the simple code. What is the simple code? You have to find how many ones are there in binary representation of a number n. It will have the same number of ones as n by 2 if n is even. Okay, it will have same number of ones as n by 2 plus 1 if it is odd. That's it. These two line of code is the entire code. Okay, so let's quickly code it. So now we'll just do it in O of n time complexity. Okay, so what we are doing, we are building the answer vector, right? So what we'll do, so what is answer of I? Very simple, just look at answer of I by 2. And if, okay, so this will be what? This will be for even numbers. For even numbers, what is happening? Answer of I is equal to answer of I by 2. Okay, if I is even, so if I mod 2 is equal to 0, then it is just this. Okay, else answer of I is equal to answer of I by 2 plus 1. Okay, that's it. This is simple logic. Now let's submit and see if it's working. So what is the best thing about this? The time complexity is just O of n. Okay, it's working. Thank you for being patient and listening.